Download this code from codegive.com, link in the description below. OK, let's dive deep into inline functions in C/C++, covering everything from their basic purpose to more nuanced considerations. This is a comprehensive guide equivalent to a detailed lecture on the topic. C/C++ Programming Course, Lecture 73, Inline Functions. Introduction, the function call overhead. Before we understand inline functions, it's crucial to grasp a fundamental aspect of function calls in compiled languages, like C and C++. Whenever you call a function, the following operations typically occur. 1. Stack frame setup *. The calling function prepares a stack frame for the called function. This frame holds * arguments being passed to the function. * the return address, where execution should resume after the function completes. * space for local variables within the called function. * the previous frame pointer, for stack unwinding. 2. Argument copying * the values of arguments, unless passed by reference or pointer, are copied onto the stack. 3. Jump to function * the program counter, instruction pointer, jumps to the memory address where the called function's code resides. 4. Function execution * the called function executes its instructions. 5. Return value, if any. The function calculates the return value, if any, and places it in a designated register or memory location. 6. Stack frame cleanup * the stack frame created for the called function is deallocated, popped from the stack. The program counter is set to the return address. 7. Resume execution * the calling function resumes execution from the point where the function call was made. It retrieves the return value, if any. This whole process, while necessary for modularity and reusability, introduces a certain overhead. For very small functions that are called frequently, this overhead can become a significant performance bottleneck. 2. What are inline functions? An inline function is a suggestion to the compiler to replace a function call with the actual code of the function itself at the point where the call is made. Instead of the function call overhead described above, the compiler effectively inserts the function's body directly into the calling code. This is often called inline expansion. 3. Why use inline functions? Benefits. Performance improvement *. The primary benefit is potentially improved performance. By eliminating the function call overhead, stack frame setup, argument copying, jumping to the function, etc., inline functions can speed up code execution, especially for frequently called, small functions. Optimization opportunities * When a function is inlined, the compiler has a larger chunk of code to optimize as a single unit. This can lead to better instruction scheduling, register allocation, and other optimizations that wouldn't be possible if the function was treated as a separate entity. Code clarity. Sometimes in some cases, inlining very simple functions can improve code readability by eliminating the need to jump to another part of the source code. However, excessive inlining can make code harder to understand and debug. 4. How to declare inline functions in C/C++. *C*. In C, you use the inline keyword before the function's return type. *C++. C++ offers two ways to declare inline functions. 1. Using the inline keyword, same as C. 2. Defining the function within the class definition *. If you define a function directly within a class definition, it's implicitly treated as an inline function. This is common for simple getter and setter methods. Important considerations and limitations. Suggestion, not a guarantee. The inline keyword is only a suggestion to the compiler. the compiler is free to ignore the suggestion and treat the function as a normal, non-inline, function. There are several reasons why a compiler might not inline a function. Asterisk function complexity. Asterisk if the function is too large or complex, the compiler might decide that inlining it would increase the code size too much, potentially leading to performance degradation, due to cache misses, etc. Asterisk recursive functions. Asterisk recursive functions generally cannot be inlined directly, although tail recursion optimization might be possible in some compilers. Asterisk function pointers. Asterisk if the function's address is taken, example assigned to a function pointer, the compiler usually cannot inline it because the function needs to exist as a separate entity. Asterisk debugging considerations. Asterisk inlining can make debugging more difficult, as the code is no longer organized in distinct functions. Asterisk compiler optimization settings. Asterisk compiler optimization levels can influence inlining decisions. Asterisk code size. Asterisk inlining can increase the size of the executable, especially if the function is called from many different places. This can lead to larger executables, increased memory usage, and potentially slower execution due to cache misses, when the code is too large to fit efficiently in the CPU cache. Asterisk compilation time. Asterisk excessive inlining can increase compilation time, as the compiler has to perform more work. Asterisk C++ specifics. Asterisk virtual functions. Asterisk in C++, virtual functions cannot be directly inlined because their actual implementation is determined at runtime through dynamic dispatch, readable lookup. However, if the compiler can statically determine the concrete type being used, example through static analysis, it might be able to inline a call to a virtual function. Asterisk templates. Asterisk templates are often used with inline functions, especially in header files. When a template function is instantiated with a specific type, the compiler can generate an inline version tailored to that type. 6. When to use inline functions, guidelines. Asterisk small, frequently called functions. Asterisk the best candidates for inlining are small functions, a few lines of code, that are called frequently within performance-critical sections of your code. Examples. Asterisk simple getter/setter methods, as shown above. Asterisk basic mathematical operations, example calculating the square of a number. Asterisk simple comparisons or logical operations. Asterisk header files. Asterisk if you define a function in a header file, it's often a good idea to declare it as inline. This allows the compiler to inline the function in multiple compilation units without violating the one definition rule, ODR. Asterisk profile before inlining. Asterisk don't blindly inline every small function. Profile your code to identify performance bottlenecks. Inline functions that are causing a significant performance impact. Premature optimization can be a waste of time and can even make your code slower. 7. Code examples. Example 1, simple C inline function. Example 2, C++ inline functions in a class. Example 3, C++ template and inline function. Example 4, compiler refusal of inlining, illustrative. This example is intended to show a situation where a compiler might refuse to inline, even if asked. The precise behavior depends on the compiler and its optimization settings. In this case, complex function is too large and complex. A compiler might decide that inlining it would bloat the main function and hurt performance. Use a disassembler to check if function is inlined or not. 8. Practical considerations, compiler flags and tools. Asterisk compiler optimization levels. Asterisk most compilers have optimization flags, example O2, O3 in GCC and Clang, /O2 in Visual Studio, that control the level of optimization. Higher optimization levels often enable more aggressive inlining. *disassembler/debuggers *use a disassembler, example OBJDump, GDB, Visual Studio's debugger, to examine the generated assembly code. This will show you whether the compiler actually inlined a particular function call. *profiling tools *use profiling tools, example prof, perf, Visual Studio's profiler, to identify performance bottlenecks in your code. This will help you determine which functions are good candidates for inlining. 9. Conclusion. Inline functions are a powerful tool for optimizing C and C++ code. By eliminating function call overhead, they can improve performance, especially for small, frequently called functions. However, it's important to use them judiciously, as excessive inlining can increase code size and compilation time. Always profile your code to identify performance bottlenecks and use a disassembler to verify that the compiler is actually inlining the functions you expect it to. Remember that inline is just a suggestion, and the compiler ultimately decides whether or not to inline a function.